Hello and welcome back to Quantitative Reasoning Online, Lesson 15b, All Things in Moderation, in our tutorial. Yeah, we finished 15a the other day, and let's do 15b next. So 15b is an exercising section. So let's see, preview. The intent is to distinguish observational from experimental. Determine which is the explanatory and which is the response variable. Distinguish quantitative and categorical variables. Identify a flaw in experimental design study. And define a confounding variable. Big picture, we call observational are experiments where we have no treatment. No manipulating variables. Experimental studies, on the other hand, usually involves a treatment, which involves a variable being manipulated. Our explanatory and response variables. That is what we're looking at. Explanatory basically explains the response. What variable studied could lead to a given response? Quantitative. Data that I can do useful math with. Such as mean, median, standard deviation, etc. Categorical. It's some quality of the subject. Can't really do math on it. And we'll discuss in this section the flaws, and we'll also look at confounding variables. Confounding variable many times considered a third variable. A hidden variable. That may hide a correlation but not a causation. A hidden variable that may make two variables look like they have correlation. Here we have a study. We have a explanatory that we're looking at. With a response. But we have this confounding variable that's really influencing the two that make them look like they behave together. So a lot covered here. So let's move on. So this is all things we're going to be looking at. So the next class will focus specifically on experimental studies. You will need to distinguish an observational study from an experimental study. Tutorial for the preview of lesson 15, part B. All things moderations begin here. So consider the two exercises studies described here. Study 1. A researcher randomly divided 200 students into two groups. First group was told no exercise. Second group was told to exercise 5 hours a week, at least 5 hours of exercise a week. At the end of 2 months, the heart rates of each participant in each group were measured at rest. It was found that the group that exercised 5 hours a week had a significantly lower average heart rate. So let's see, we had looking at time, heart rate, and this was no exercise. This was 5 hours of exercise. And I'm just making stuff up here, but hey, don't exercise. You would basically expect the heart rate as you measure over time to be constant. And it looks like they're going to claim that there was some decrease in heart rate over time, specifically 2 months. And when saying at 2 months' time, there was a significant lowering of average heart rate. Study 2. Researchers gathered 200 high school students randomly and asked them how long they exercised each week. So we had 200 students surveyed, and how much they exercised at least how long they exercised and measured their heart rates at rest. Okay. So they got data, and of course, heart rate, time of exercising, and they get some data. And they found somewhere here at about 5 hours, there was a significant reduction in heart rates. Okay. Now let's see. This one, which is a survey, no influence was put in. So this would be an observational study. And this one, because there was some treatments, this would be an experimental study. So study 1, experimental. Study 2, observational. Oh, which was experimental and why? We kind of told this one with study 1, we had a treatment. We varied exercise time between two groups. There's a difference between them. And this, like I said, this was just basically a survey. What we said, or what was said. This is explanatory and response variables in the studies. Let's see, explanatory. Looks like exercise. And response would be heart rate. Oh, right. B. View the prompt and enter response. State whether the variable in the studies are quantitative or categorical. Heart rate. Exercise time. Both are measurable. Both I can do math on. I can find a mean exercise time or mean heart rate. That's meaningful. In this case, that will make them both quantitative. Because both something we'd measure. That's what C. Yep. Now let's identify a flaw in study 1. A researcher randomly divided 200 high school students into groups. Okay, it's plain 1. First group told not to exercise. The second group was told to exercise at least 5 hours each week. At the end of 2 months, the heart rates were measured. It was found that the group that exercised 5 hours a week had significantly lower heart rate average. So again, look at all the measurements were done at the end of 2 months. So we have 100 students, no exercise, measure their heart rates. And probably get like a mean average heart rate. Let's say then in 2 months, then we had 100 students. We did exercise. Again, have that 100. Measure their heart rates. And compared. And supposedly they found this one was significantly lower than that one. Alright, so what's the problem? Let's read the list here. The participants should not have been randomly assigned to groups. No, that's good, because you don't want to have one group be all athletes and the other group be all non-athletes. You want to mix. Participants should not have been told how much to exercise. Well, we got to have something to measure. So basically, what we were telling them was the treatment. Well, that was the treatment, so we have to tell them what to do. See, the participants' heart rates should be measured both before and after the studies. So this was all done, like I said, these were all done after the study. It'd been nice to know what it was before the study. This is just a what if. No. For these exercise guys, maybe they were already heavy exercisers. Or maybe the other ones were heavy exercisers and we told them to not exercise. So it's always good to have a before and after, even among your what's called a baseline. There was no baseline. To see if there really was a change among the population. Like now we compared two sample populations, exercisers and non-exercisers, but we really shouldn't see if there was a change within the exercise people themselves. Going back to the very first slide, if you're not exercising over time, you really won't expect much of a change of heart rate from time 0 to 2 months. If you really need to know, for the exercisers, between 0 and 2 months, did they start up here like the non-exercisers and then went down? Or because you already got a very physically fit group to begin with, again, no major changes occurred. So it's nice to know what's happening within the population itself, your sample population. So a baseline is important to have. So that was the flaw, the defect. Didn't have a baseline. Statistics sometimes a confounding variable appears in a statistical model. Search for information for examples of confounding variables and write a definition in your own word and give 2 brief examples. Be sure to give your source. Bring a response to the next class. No, that's not very practical in online here. Suppose in the future, note to self, this would probably make a good discussion board question. Make a note. Pause. Like I said earlier, confounding variable, kind of like those monkey wrench. Here's an example that's given. It's a classic example. Someone did a study on ice cream cone sales at a beach stand. They also looked at drowning deaths, or deaths by drowning. And they did a study. And they found as ice cream sales increased, drowning deaths increased. So obviously, the sales of ice cream causes drowning deaths. So the conclusion: ice cream cone sales results in drowning deaths. Real good correlation. Therefore, you must have causations. Well, the problem is a confounding variable. There's a third variable that actually controls both of these two variables that we're trying to compare. And it's basically temperature. The real analysis is, as temperature increases, ice cream sales goes up. It gets hot. As temperature increases, drowning death also goes up because more people go in the water. That's a confounding variable. It makes two variables, the explanatory being ice cream, and the response is people drowning deaths. So to reduce drowning deaths, reduce sales of ice cream cones. But that's because there was a third confounding variable, temperature, that was really the driving factor. And we take care of that by trying to control all variables that may affect an analysis. So let's see. How confident you can distinguish observation from experimental. Remember, experimental has a treatment, observational does not. How confident are you that you can determine explanatory and response variables? Pretty confident. Whether it's quantitative or categorical, again, is it describing a quality of the subject or the experimental unit? Or is it a number that I can actually do some math on? Trying to identify flaws in its design, somewhat. Defining a confounding variable, always somewhat on that one too myself. And that is 15B's preview. We did this, we worked on that, discussed that, analyzed that, and discussed that. And that's all we have. So let's close this down, and I'll see you shortly. Go look over on your own the tutorial. Actually go on the internet and check on confounding variables and look it over and see if you can find more examples to better explain to yourself what a confounding variable is and what it does. And with that being done, I'll see you for question 1 and 2.